Okay, so here we have another sample problem. So here it says the cross-section of a long conducting cylinder with inner radius A equals 2 cm and outer radius B equals 4 cm. The cylinder carries a current out of the page and the magnitude of current density in the cross-section is given by J equals C R squared. Okay, so this is not uniform. This is not uniform. So we need to do some integration. We can expect. So what is the B field at the point that is 3 cm from the central axis of the cylinder? Okay, so this is actually the amperance loop. Okay, so for this amperance loop, we need to consider the I enclosed in that part. Okay, so I enclosed will be integration of J dot dA, or J times dA. Okay, we already assume that J and dA actually points to the same direction. J and dA. Okay, so in that case, in this case, okay, we assume the amperance loop to be like this, to be clockwise. We can also assume that the I should be pointing into the page. The I should be pointing into the page, so that it matches the direction of the right-hand rule. Okay, so that it will make everything positive. Okay, so in that way we can plug in the J to be CR squared here. Okay, integration of CR squared, and then dA, I don't know whether you still remember, dA for polar coordinate will be r d theta. Okay, so we have r d theta double integral. And then for dr, we don't integrate from 0 to r. Here, we try to integrate from, this one is A, this one is small r. Okay, so from A to small r. So here, let us try to put prime here, so that all this W variable doesn't conflict with this one. Okay. And then for the d theta, we still integrate from 0 to 2 pi for the whole 360 degree. Okay, so yeah, so just wait a moment. Here it actually mentioned that the current is out of the page. The current is out of the page. So that, okay, so here, this one should be like this. This one should be like this. Okay, however, the DA should be into the page. The DA should be into the page according to the right-hand rule. So in such a way, we have a negative sign here. We have a negative sign here throughout the computation. So finally, we have a negative C, and then we have integration of r prime cube. Okay, r prime square and r prime. So r prime cube, dr prime from A to r. And then integration of a d theta 0 to 2 pi. Okay, so finally this one is r to the 4th power over 4. So minus c, and then r to the 4th power over 4 minus a to the 4th power over 4, and then times 2 pi. So the answer will be negative pi c over 2. And then r to the 4th power minus a to the 4th power. Okay, so this is only the I enclosed. So here we have I enclosed equals negative pi c over 2 r to the 4th power minus a to the 4th power. So the remaining stuff is the Ampere's law. the Ampere's law. Okay, so this is A. This is the Ampere loop. This is the Ampere loop in this direction, counterclockwise. And then the current is into the page. The current is out of the page. Sorry, the current is out of the page. So in such a way, we have integration of a B dot ds equals mu 0 I enclosed. Okay, so similarly, we have B field, the B field. Okay, so this here we have the loop like this. We have the loop like this. This is counterclockwise, and then the current is the current is out of the page. Sorry, this loop is clockwise. It should be clockwise. And then the current is out of the page. So you can imagine the loop is like this. Positive direction should be into the page, but the current is out of the page. So you can expect here is the B field. The B field is negative. The B field is negative. Okay, so in that way we also have a B times 2 pi r. Okay, this is small r. This is small r, and then equals mu 0 I enclosed. So we have B equals mu 0 over 2 pi r times I enclosed, and then we can plug in the expression here. So we have a mu 0 over 2 pi r, and then times pi c over 2, and then r to the 4th power minus a to the 4th power. We have a negative sign here. Okay, so here we can cancel this pi with this pi, and nothing else. So we have a negative mu 0c over 4r, and then we have a r to the 4th power minus a to the 4th power, and then we can plug in all the numbers. So this is nothing but 4 pi times 10 to negative 7, and then c, what is c? C is these values, 3 times 10 to the 6th power, 3 times 10 to the 6 over 4. R is 3 centimeter. R is 3 centimeter. A is 2 centimeter. So here we have times 0.03, and then 0.03 to the 4th power minus 0.02 to the 4th power, like this. So this is nothing but minus 20 mu j, minus 20 mu j. And as much as the loop is in this direction, and then what we get is B is a negative value. So which means in that case B is counterclockwise. Okay, so B is counterclockwise 是逆时钟的，也就是说，他一开始定义这个 Ampere loop 的方向，他故意把它定义成跟那个电流不匹配的方向，所以有很多东西都产生一个负号出来，但是它还是会正确的。如果你想不要那么别扭，是中间I enclosed 是负的 ，B 又是负的，那你可以定义这个Ampere loop 是反方向的，那你推导出来所有的值都是正的，那就得出来的结果还是一致的。所以意思是你怎么定义这个 loop 的方向是无所谓的，那只要你把符号判断正确就好。当然，你觉得说这边有负号我不喜欢的话，你全部算正的，然后你按照自己的想法去 去想这个 B field 的方向也是可以啊，因为你单纯知道这个 I 是往out of the page 的方向的话，那你用右手盯着，你很快就知道说这个 B field 应该是历史中的，就不需要管那些其他东西。Okay, so up till now, any questions? Okay, so yeah, so here, okay, so here we talk about something called a solenoid. Solenoid 就是一个线圈啊，就是一个线圈。Okay, so a solenoid generate B fields. Something similar to a capacitor. A capacitor will generate E field, but a solenoid will generate B field. So yeah, so this is quite complicated at the first glance. So here it says for the point very close to a turn, the wire behaves magnetically almost like a long straight wire, and the line of B there are almost concentric circle. What it means for this one, for this part, it actually means this part, or the other part here. Okay, so it means that if you just zoom in, ignoring all the other stuff, okay, which means that you are close to the wire, then you will see the B field is like concentric circle around. OK， 就是看起来如果你看得很靠近它的话，它看起来就像一根无穷长的一个导线，有带电流还是直的，虽然它是圆柱形的一圈一圈上去的，但是如果你看得够近的话，它就像一个无穷长的导线，所以在靠近的地方你就看到一些同心的B field B field line， 所以是这个部分。Okay, so and then for the other part, okay, the field tends to cancel between adjacent turns. Okay, so it means the position here. Okay, so between adjacent turns. Okay, so or maybe you can observe here. So because for this one, okay, it would generate B field like this. Okay, so at this point, the B field generated by this part is pointing upward, and then for this part, at this point is pointing downward. Okay, so if it is actually the midpoint between these two wires, okay, the magnitude will be the same and then point to the opposite direction. So it perfectly cancel each other. So which means that near this part, okay, or actually near that region, okay, so the B field are quite weak at those points. Okay, and then finally this part, okay, at points inside the solenoid and reasonably far away from the wire, B is approximately parallel to the central solenoid axis. Yeah, maybe I use this one, okay, to specify. Okay, so it actually means that this part. Okay, this part, which means that it is relatively far away from the wire, and also between actually inside the solenoid. Okay, so we can assume that the B field are uniform. Okay, actually, for all these B field, you can use your right hand rule to determine the direction. Okay, so for this one, okay, this one is pointing out of the page, so you use your thumb pointing out of the page, your finger will be like counterclockwise, so which matches the B field line here. And for here, all these are pointing into the page, So you use your thumb pointing into the page, your finger will lie clockwise, will lie clockwise. OK， 所以这个就是线圈嘛，线圈的话就是一圈圈上来的嘛，所以它总是在上面的出来，然后上面出，应该是上面出来，上面进去，上面出来，上面进去，就是，所以它一圈一圈绕上去的，所以它实际上是，就比如说，它是这样出来的话，然后再从这个地方下去，类似像这样的，然后这里一圈一圈上去的，一圈一圈，它实际上是连接起来，它只是没有画出来，不然的话就整个图会很花，就是很乱这样。但实际上的话，线圈的话是一圈一圈连接起来的。然后 and then also for the middle part, okay, so actually this is like this is out of the page, and then also like this. So actually, for the middle part, it also follow the direction of the right hand rule. Follow the direction of the right hand rule. Yeah. So because this is into the page, so for this part is actually behind the paper. Okay. So if you use your finger, follow the direction of this part, it should be like this, and then your thumb pointing to the right side, which matches the direction of the B field inside the solenoid. So for any of the direction of B field, you always use the right hand rule to determine direction. Okay, so here we try to use the Ampere's law to find the expression of the B field inside the solenoid, and also we make some approximation. To make the computation easy enough. Okay, so the first is that we assume the B field is uniform within the solenoid. Okay. And then it is perfectly zero outside it. OK， 就是类似电容啊，电容的话，其实它不一定是很均匀的。当时的话也是假设说要无穷大的平衡板，它才会产生一个均匀电场在两个板之间。但是实际上电容也是有限大的嘛，所以在计算的时候也是假设说平衡板中间就是均匀的，外面就零，但是实际上外面也是有一些所谓的 fringe 的 E field 边际的 E field 实际上它不是零，但是为了计算方便就忽略了。现在这个情况也是类似那样。Okay, so here, this is the cross section. This is the cross section of a solenoid. Okay, so here we have all these current pointing out of the page. We have all this current pointing into the page, and then this is the Ampere loop. Maybe I use blue. Okay, this is the Ampere loop. Okay, this is a rectangle. One side is inside the solenoid, and then also parallel to all this B field, and then one side is outside, and then one side is perpendicular to it. Okay, so here we would like to apply the Ampere's law for this Ampere loop. Okay, so for the left hand side, the line integral for the closed loop, it can be separated into four parts. Okay, from A to B, B to C, C to D, D back to A. So we have an integration. Okay, so here we don't have a circle here for all these four integration because it's only a line integration for a straight line. So here for the line integration from A to B, the line integration from B to C, so on and so forth. Okay, so for B, C, C, D, D, A, okay, so for let's say this one, DS, for this one, ds is pointing upward. B field is pointing to the right side or 0 here, so b dot ds are always 0. And similarly for this case, so we can see that dA, okay, this one and also this one is 0. And similarly for this part, ds is pointing to the left side, and then b field is 0 outside the solenoid. So similarly, this one is also a 0. Okay, so this 1, 2, 3 line integration is are all zeros. Okay, so which means this is 0, this is 0, this is also 0. So the only thing is this one from A to B. From A to B, okay, we have ds pointing to the right side, and then the b field also points to the right side. Okay, so b dot ds become b times ds, and b is uniform. So which means it turns out to be the integration of A to b dot ds, okay, b dot ds, b and ds point to the same direction, so it becomes b times ds, and b is a constant, so it becomes b times integration of ds from A to b. So which means this is nothing but the length of this line. Okay, so from here to here, the length is h, so bh, like this. So okay, so this is nothing but bh. So on the left side we have bh. Okay, we have bh on the left side equals mu 0. And then here I enclosed will be I times n times h. I times n times h. What it means here, what it really means is that n here is the number of turns per unit length. Just as what I mentioned in the previous chapter, it always use capital N to specify the total number of turns, and then small n refer to the turn density, which means the number of turns per unit length. 小写的 n 就是指这个线圈的密度，大写的 n 是总的圈数，所以小 n 的话是每单位长度的话那个圈数，单位长度的圈数。OK， 所以这里的话就是说 in I enclose is actually counts all this I. Okay, every dot here is an I. So we need to count how many number of I here. Okay, so actually it is n, small n times the h. Small n times the h will be the total number of turns, or total number of current going through this ampere loop. So this h and this h cancel each other, and finally it becomes b equals mu 0 in. So this will be the B field generated by a solenoid. So so mu 0 is a constant, 4 pi times 10 to the 7th, and then I. Okay, so we assume you fix it, or maybe it means that you can control the current. Okay, so it actually means that the B field is proportional to the current. And then n depends on the geometric shape. Okay, it depends on the turn density. Turn density. So after it is created, then it is fixed. This n is fixed. So the B field generated by this solenoid is proportionally to the current that you can control. Or you can, if you can make it better, okay, you can pack more turn in unit length, then probably you can also generate a larger B field. Okay, so another one is called the toroid. Okay, so here we try to bend the solenoid until its two ends meet， 就是把一个 solenoid 把它头尾相接， 变成一个像一个手链或者手链这样的一个形状啊，就是像一个甜甜圈这样的形状。Okay, so in such a way, we can yeah. So this is the cross section of this toroid, and then we try to assume the ambient loop as this orange circle, and then also we define the direction will be like that. Okay. So in such a way, we apply the Ampere's law for this ambient loop. So on the left side is nothing but integration of b dot ds become this one, b times 2 pi r. Okay, because b and ds parallel to each other, and b is uniform over the whole ambient loop, so it becomes this one. And then on the right side, mu 0 I enclosed. Mu 0 I enclosed, so mu 0 is here, and then for every cross here, it is I. This is I, all the way I. So we only count how many number of cross is inside. Okay, so this n is the total number of turn. This n is the total number of turn. N is the total number of turn. Okay, so in that case, we just move 2 pi r to the right side, so b equals mu 0 I capital N over 2 pi r. So in contrast to the situation for a solenoid, b is not constant. Okay, for a toroid, the b field inside a toroid is not uniform. Okay, it related to the radius from this center to the point you concern. Okay, so here we have a sample problem. So a solenoid has length L equals 1.23 meter and inner diameter D. Okay, it carries a current I, and then it consists of 5 close packed layers, each with 50 turns along the length L. What is B at this center? Okay, so B equals mu 0 I n. So mu 0 is 4 pi times 10 to negative 7. And then I is this one, 5.57. And then times n. So it says actually it has a 5 pack. It has 5 pack, and then with 850 turns for a single pack. So we have a 5 times 850. This is the total number of turns. So we need to divide the length. The length will be 1.23 meter. 1.23 meter. It has nothing to do with this diameter. It only related to the length. Okay, so the whole thing becomes a small n. So in this case, the B field will be 2.42 times 10 to negative 2 Tesla. Okay. So this is just a simple sample problem to make use of this B equals mu 0 I n. Okay, so here we also talk about a current carrying coil as a magnetic dipole. 就是说一个带电流的线圈，其实它是一个 magnetic dipole。然后这个 magnetic bar 这个磁棒也是一个 magnetic dipole。所以它的意思是说，其实在这个产生磁场这个或者产生 B field 这个特性来说，这个线圈跟这个棒 其实是等效的啊，其实是等效的。甚至我们调整这个 I 的大小的话，或者是这个线圈的半径的话，其实我们可以产生一模一样的 B field 都可以。Okay, so so here is a magnetic dipole at point P. So the magnetic dipole, or the B field generated by the magnetic dipole along the z-axis will be mu 0 over 2 pi times mu over z cube. The expression looks like this. Okay, mu is the dipole moment, and then z is the z-axis component. Okay, we consider this plane with this current loop will be 0 for z. Okay, 就是这个是 z 等于0的平面，这个地方是 z 等于0，那这个是 z 轴哈。那看到这个式子的话，是不是还记得？好。So do you still remember? Okay, so the electric field generated by a dipole will look like this. Okay, so comparing with this one, okay, so we have 4 pi epsilon naught mu 0 over 2 pi, and then we have a 2 here. Okay, so if we actually cancel, so we will get E equals 1 over 2 pi epsilon naught, and then P vector over C cube. Okay, so we'll compare this one and this one. C cube. This is the magnetic dipole moment. This is the electric dipole moment. Okay, 2 pi. Okay, we change epsilon naught to 1 over mu naught. Okay, so this 1 over mu naught in the denominator go to the numerator. Okay, so yeah, these two a duality 就是那个二象性嘛，又或者是对称的。Okay, so actually we will derive it a little bit later, but here we also mentioned that we have two ways in which we can regard a current carrying coil as a magnetic dipole. So for the first case, it experiences a torque when we place it in an external magnetic field. Okay, so yeah, the external magnetic field or the external B field is generated by this N and then this S. Okay, so we have B field this way. And then if we place a current carrying coil here, then this coil will have a torque, so that it will rotate. It will rotate like this. And then for the second case, it generates its own intrinsic B field given for the distance point along its axis. Okay, so both these magnetic bar and the current coil can generate actually the same pattern or similar B field pattern. Okay, so here we try to simply derive this expression using the Biot-Savart law. So here we assume we have a carrying current coil, but yeah, so this is just a cross section, so that we only see this. We only see a line here, but actually this is a coil. Okay, so in that case, we have the current. Okay, the current here is pointing out of the page. This is pointing into the page at this point. Okay, so for Biot-Savart law, dB equals mu c over 4 pi I ds cross r hat over r square. Okay, so for example, this is ds is pointing out of the page, and then this p is what we concern, and then this z is a known variable, but r is not a known variable. Okay, but actually in this Biot-Savart law, what we have is this r, or this r hat. Okay, so r hat is counting from ds pointing to the point we concern. So r hat pointing to this side, and then ds cross r hat is something like ds cross r hat. Okay, your thumb is pointing to the top left. Okay, so db generate point p by this segment is like this. And then for this one, this is ds prime. Okay, this is ds prime. Okay, this is pointing into the page, and then this is the r hat for it. Okay, so if you use your finger pointing into the page and then cross it to the r hat, your thumb is pointing to the to this side, to this side. Okay, so so actually this is alpha, this is alpha, this is perpendicular. So this is also alpha. So in such a way, this one and this one, for the perpendicular component, it cancels. We only count the dB parallel. So for the dB parallel, we have mu 0 I over 4 pi and then cosine of alpha. Oh, this one is cosine. This sine divided by this one is cosine of alpha. And then ds r square. And then r, in this right angle triangle, r is square root of z square plus capital R square. Capital R is the radius of this coil. So we have R to be like this. So we can plug in this R to here, and then cosine alpha. Cosine alpha is this one. Cosine alpha is capital R over small r. Okay, capital R over small r is this. So we can put these two into there. So dB parallel will be mu 0 I over 4 pi, and then r, okay, cosine alpha, we have an r ds here, and then here we have r square, and then another r here, so altogether we have this one to the 3 over 2 power. So finally, b will be integration of dB parallel, so this one here, and then r here, and then this one here. So we integrate ds, okay, so all the other stuff are independent to ds. So this ds is nothing but, this one is nothing but 2 pi capital R, 2 pi capital R. So this 2 pi and this 4 pi partly cancel, become this 2, this r and this r becomes r square here. Here we also assume that we have a z is much larger than capital R, so that we can just ignore this one. So c squared to the 3 over 2 power becomes z cube, okay, becomes z cube going to here, becomes z cube going to here. So finally, if z is much larger than r, it becomes mu 0 I over 2, and then r squared over c cube, like this. So here we try to construct the magnetic dipole moment back. Okay, if you still remember, the magnetic dipole moment mu will be NIA. So for the A here is a circle, so NI pi r squared. And here we only have n equals 1 here, but n can be any variable. So here we just ignore this n at this moment, and then I pi r squared will be the mu. So here we try to multiply pi here and multiply pi here, so that we change nothing. But here we can construct this I pi r squared out, become the mu. Okay, so here we have mu 0 mu, and then over 2 pi c cube, okay, which is actually this equation, Okay. Yeah. So. Okay, so it still takes time to